Let's consider the colligative property of freezing point depression. The freezing point of a solution is lower than the freezing point of the pure solvent. The difference between the freezing point of the pure solvent and the freezing point of the solution is the freezing point depression. The equations to find the freezing point depression can be presented in a few ways, but remember, the freezing point of the solution must always be lower than the freezing point of the pure solvent. Check that your final answer is consistent with this fact. This table lists the molal freezing point depression constants, Kf, for a few solvents. Let's compare freezing water to freezing salt water. Pure water freezes at 0 degrees Celsius. Dissolving salt in water disrupts the ability of water molecules to stick to each other to form ice. As a result, the temperature must be lowered. In other words, a lower freezing point is needed to make the water molecules slow down enough to interact and attach themselves to form ice. Let's consider the colligative property of boiling point elevation. The boiling point of a solution is higher than the boiling point of the pure solvent. The difference between the boiling point of the solution and the boiling point of the pure solvent is the boiling point elevation. The equations to find the boiling point elevation can be presented in a few ways, but remember, the boiling point of the solution must always be higher than the boiling point of the pure solvent. Check that your final answer is consistent with this fact. This table lists the molal boiling point elevation constants, Kb, for a few solvents. Let's see how freezing point depression and boiling point elevation are displayed on a phase diagram. The blue lines in the graph represent the pressures and temperatures for the phase diagram of the pure solvent. The red lines in the graph represent the pressures and temperatures for the phase diagram of the solution. Note that the fusion curve along the solid and liquid phases is shifted to lower temperature due to freezing point depression for the solution. Also note that the vaporization curve along the liquid and gas phases is shifted to higher temperature due to boiling point elevation for the solution. Let's consider the colligative property of osmotic pressure. Osmosis is the flow of solvent from a solution of low concentration into a solution of high concentration. A semi-permeable membrane allows solvent, but not solute, to flow through it. As shown in this figure, a solution is on the left side of the semi-permeable membrane and pure water is on the right side. Remember, there is a natural drive for materials to mix. Water molecules pass through the semi-permeable membrane to mix more with the solution, diluting it. Again, there is a natural drive for materials to mix. The mixing continues until osmotic pressure is reached. Osmotic pressure is the amount of pressure that is needed to stop osmotic flow. Osmotic pressure depends on molarity concentration, whereas freezing point depression and boiling point elevation depend on molality concentration.